I'm Anil Kumar. Let us discuss higher order derivatives and take some examples to practice. The equation here is the position function gives s in meters as a function of time t in seconds. Find velocity and acceleration as a function of time. Assume t is greater than or equal to 0. Now velocity is first derivative of displacement. Let's write down velocity as equal to first derivative of position vector or displacement, and acceleration is first derivative of velocity or second derivative of position. So in higher order derivatives, position, velocity and acceleration are very important as real-time application questions. Now here we have three different types of questions. The first one represents vertical movement. So whenever you're talking about throwing an object right up, it will fall down because of acceleration due to gravity. So here g is basically acceleration due to gravity, and the value is 9.8 meters per second square. So you must have seen many formulas with half of 9.8, which is 4.9, right? Rounded to 5 when this formula is used for any object's height with respect to time. So that's the function which we'll look into. The second function here is product of two. So the position is shown as product of two functions. Purposely we have taken square root functions because their derivatives make it slightly difficult to simplify. Now whenever you have a question like this, I will suggest rewrite the equation in the expanded form, since you do have to simplify these equations. So rather simplifying the derivatives, let us open this. We may get 6 terms, okay, but much simpler derivatives. And part C is displacement in the form of a function divided by another function, where again I've taken square root function. It is only for your practice. You should assume t greater than or equal to 0. This is when square root t is valid, correct? That's the domain for square root functions. Perfect. Even when we consider many applications of speed, velocity and acceleration, we consider time to be greater than 0. So let us take them one by one and solve. S of t equals to S0 plus V0 t plus half gt square. Now in many application questions, S0 is termed as initial position. V0 is treated as initial velocity. G is acceleration due to gravity. In MKS units, it is 9.8 meters per second square, right? So basically these three are constants. So all these three are constants. Now I think becomes easier to find the derivatives of this function, since we know these are constants and the only variable here is time. Perfect. Normally when we consider this equation, we are actually trying to understand a question which relates to height of an object. Height of an object. So it could be thrown vertically up, coming down, or it could be kind of like this, right? So that is the kind of situations where we use this particular equation. So I hope that gives you significance of this equation. So you'll get across many questions, very important questions based on this. So here is the general solution. We know that the position, it could be vertical or horizontal. In this case, it seems to be vertical, is initial position from where the object is thrown, initial velocity, the velocity with which it is thrown, plus half times gt square, and that gives you the acceleration. Because of the gravitational force, the object really returns to the ground, speeding, correct? Derivative of this will give us the velocity So velocity is equals to derivative of position. Since these two are constants, derivative of this will be 0. And here we'll treat V0 as constant. So we get V0 plus half times G is a constant times 2t, right? You could simplify this as initial velocity plus gt, right? So that is the expression for velocity. Acceleration, as you know, is the derivative of velocity, right? So we could write this as derivative of velocity. Since initial velocity is a constant, its derivative is going to be 0. So we are left with g here. So as I was saying, it makes sense. G is acceleration due to gravity. Perfect. So that is how this equation is analyzed. And it has huge application whenever we are studying projectile motion, right? So whenever you're working with projectile motion, it is of great importance, correct? Now from this equation, you could actually find when is velocity is 0, right? So the time when velocity is 0, that also gives you the maximum height. So one of the application question could be find time when velocity equals to 0, or we could also say find maximum height. So that will be the time will be taken from here, right? When the velocity is going to be 0, at this turning point, velocity is going to be 0. So if you substitute that time here, you can find the maximum height of an object. Great. So that is a huge application of this question. So we'll not get into this. There will be many questions. I'll provide you link of which you can solve. Now let's look into the next type of question. At times you may get a function like this, where displacement is given product of two factors. I will suggest that expand it. So when you expand, t times 2t square will be 2t cube, just multiply, minus t square, and that gives you minus t to the power of 1 plus half, 3 over 2. Is it okay? Now with minus 2, 2 times 2 is 4, t to the power of 2 plus half, which is 5. So 2 plus half means 5 over 2. And then that gives you positive 2, t to the power of 3 by 2, 1 plus half that is. And when you multiply the last term, you get positive 2 times t. If you, now you have 6 terms, okay. But derivative of these 6 terms is much simpler. You can always combine these two and then rewrite the function as 2t cube minus t square plus 2t minus this gives you plus t to the power of 3 by 2 minus 4 t to the power of 5 by 2 plus 2t, correct? So that becomes your equation in simplified form for displacement, right? So displacement units are going to be in meters, for example. Then velocity is rate of change of, let me write like this. Velocity is rate of change of displacement, right? So let's find derivative of this. So you get 6t square minus 2t plus 3 over 2 t to the power of 3 by 2 minus 1. So that means half, square root that is, minus 4 times 5 by 2 t to the power of 5 by 2 minus 1, which is 3 by 2 plus 2, correct? So that becomes your equation. You could simplify this and write this as 6t square minus 2t plus 3 by 2. If you want square root, write square root minus 4 times 5. This could be simplified. That goes 2 times, right? So you get 10 cube roots. So you may write like this only. Okay, no problems. Now let's find the acceleration. So acceleration is derivative of velocity, which is 12t minus 2 plus 3 over 2 times half t to the power of minus half minus 10 times 3 over 2 t to the power of 3 by 2 minus 1, that means half, right, plus 0. Constant derivative is 0. This could be simplified and written as 12t minus 2 plus, that is 3 over 2 times 2 is 4 square root t minus 5 times 3, 15 square root t, right? So that becomes your final derivative. Perfect. So I'll advise you to not apply product rule, rather expand and then simplify. It becomes much, much simpler. So let's move on and take up the next question. So as a very special day today, being holy, I'm going to introduce a small video which will take us close to nature, and then we'll get back to this question. Let's walk and enjoy the snow. It's Humber Trail. What you see here is snow all over, and also fresh tracks for deer. Let's follow and see if we can find some. Well, so much fun walking on snow. It's like sand with the weight of cotton. You can kind of kick it like this. Do you see that? You can kick it like this. Let me show you. Like this. It's so much fun. You can play all day long. That's beautiful. We have some birds. Beautiful. This is my classroom. I hope you enjoyed a short break watching nature. I actually love it, and that's my inspiration. Now let us find first and second derivative of the displacement or position function s of t, which is given to us as equal to 6t over 1 plus square root t. Now in this case, we know that time t is greater than equal to 0, and to find the first derivative, we'll apply the quotient rule. Velocity is the first derivative of displacement or position. Applying the quotient rule, which you remember, is kind of like this. If we have function, u over v, in that case, derivative of u over v is v square, derivative of the first function times v minus u times derivative of the second function, correct? So in short, just a small reminder. So we'll square the denominator, which is 1 plus square root t. For us, derivative of 6t is 6 times 1 plus square root t. Take away 6t times derivative of 1 plus square root t. That is 1 over 2 square root t, correct? Now we can simplify this, opening the brackets. What do we get? We can actually, at this stage, also take common denominator of 2 square root t, right? Well, let us simplify it first. So we get 6 times 6 square root t plus, minus 2 divides into 6 3 times, and t divided by square root t is square root t. That becomes even simpler than what I expected. Okay, so that could be written as, within the denominator, I have 1 plus square root t whole square. Numerator, we have 6 plus 3 square root t, that is t. Correct. We can actually, if you want, you can take 3 common and write this as 2 plus square root t over 1 plus square root t whole square. To find the second derivative, I feel this is a better and simpler expression to use, right? So let's now find second derivative for the given function. As you know, the second derivative will be acceleration, which is actually first derivative of velocity and second derivative of displacement. Correct? So let me rewrite here. Second derivative of displacement is equal to denominator square, which is 1 plus square root t, now to the power of 4 since it is already squared. Derivative of the numerator is 3 times 1 over 2 square root t times the denominator, which is 1 plus square root t whole square, minus, we get the whole term, which is 6 plus 3 square root t times derivative of this function, which is 2 times, so let me write 2 here in the beginning, 2 times 1 plus square root t, and then derivative of inside function, which is 1 over 2 square root t. Perfect. Now when you look at this, you can take few terms common. 3 could have been factored out like this, right? So we'll take 3 common. In the denominator, we can take 2 common and also square root t. So that is also common. In this numerator, 1 plus square root t is common. We have it. And now we can write down rest of the terms. So all this has been taken care of. We are left with 1 plus square root t. From here, we have minus 2. We have taken 3 out. So we are left with, let's divide them by 3. We get 2 plus square root t, as I wrote here. We have already taken this term outside and also the other term. So that is what is left here, divided by 1 plus t square root t, to the power of 4. Now 1 plus square root t, we can simplify it a bit more. So what we get here is 3 over 2 times 1 over square root t. Now in this, you can open the bracket. So we have 1 plus square root t minus 4 minus 2 square root t over 1 plus square root t. We cancelled one of them, so we get cube here. This could be written as, so in the numerator we have 3 times, and here we get 1 square root t minus square root 2t is minus square root t, right? So I could write this as, well, I could write this as, okay, let's take negative terms. I want to take negative common, but let's write. So we have minus 3 here, minus 4 plus 1, and minus square root t, right? Over 2 square root t times 1 plus square root t whole cube. Perfect. Now this could be, I don't have space here, so I'm just writing it on the top. We could take negative common. Is that okay? So we have negative 3 times 3 plus square root t over 2 square root t times 1 plus square root t whole cube. Correct? So that becomes the acceleration or the second derivative of this function. Correct? So anyway, what you realize is that whenever you are finding derivative of derivatives, it is a good practice to simplify them. And always, to find the derivative, Standard form or the expanded form is better to use rather than the factored form. We can apply product rules, we can avoid product rules and straight away apply the power rules to simplify. That helps. So that completes our video. Now I'll continue with the small clip on nature. Watch snow and enjoy. You can close whenever you feel like, and I'd like you to comment on the introduction of nature videos in between. Was it a distraction or helping? Feel free to post your comments. Thanks for watching and all the best. Snow on the leaves. Is falling from the leaves as the sun rises. Cardinals. Snow on the leaves.